Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 9, Bonding Part 1. We are in Chapter 8 of the textbook. So everybody has learned the first half of Chapter 8, so that would be the molecular geometry and shape. If you need a refresher on that, now would be the time to do so. Those of you who took this class in the 17-18 school year, this video will be a review, but not the follow-ups. And also the practice problems we do will be more detailed this year. These are the objectives for today's video. Pause here, you should draw the picture. Okay, so last year when we were talking about, this came up more with polyatomic ions, how I would tell you that it didn't matter which oxygen, for example, that you put a negative charge on when we were drawing structures of polyatomic ions, but it doesn't just apply to polyatomic ions. Sometimes there's going to be more than one Lewis structure that's valid, and if you have more than one, these structures are called resonance structures. So here, this is a benzene C6H6, and notice that it's just a very small change. It's just where are the double bonds. But the reason why this matters is because the true structure is actually a hybrid of the resonance structures. So rather than having the double bond that is on, let's say, the 1/3 and 5th carbon versus the 2nd, 4th, and 6th, it's actually evenly distributed amongst all 6 carbon atoms. That makes it very, very stable. And that's why polyatomic ions, you'll see most of them have multiple resonance structures, are able to be very stable despite having a charge to them. Pause here. I'll work through it. Another note here, if you haven't already, there are a number of polyatomic ions that's whose formulas just need to be memorized. These fall under the category. Remind me in class, and I'll give you a list if I haven't done so already. All right, I'm going to ignore lone pairs for the most part. So this is CO3 2-. So you see the brackets I'm doing? Those are just commonly used when we're writing out resonance structures. So notice how I'm really just moving the double bond around. And then you could include the extra electrons here as well, the lone pairs. But you should always label the charge. So that's carbonate. And now I'll do sulfate as well. You could do more than 3, but I'm just going to do 8. So there's one. You could pick different ones. And there are more than 3 that I could draw here. All right. Pause here. So sometimes you'll have more than one resonance structure, and they'll all be more or less the same, like you're just moving a double bond around or you're just moving a negative charge around, but that's not always the case. Sometimes you'll actually be putting the charge onto different elements, and we'll see an example of that. So formal charge is a way that we determine which resonance structure is going to be the most dominant one. Formal charge is just the difference between the number of valence electrons in a free atom and the number of valence electrons it has in the molecule. Bonds are going to count as 1 valence electron, and lone pairs will count as 2. You already have been assigning formal charges without calling it that. So in the last example, when I put the negative charge on things, I was just saying that its formal charge was -1. I'll write out like a sort of formula of sorts that if you'd like to help you remember. So the formal charge is just the number of valence electrons it normally has as an atom, minus the number of bonds, minus the number of non-bonding electrons. Pause here. So this should be pretty intuitive. We talked about it a little bit last year, but formal charge and stability. So molecules are going to be the most stable when the formal charges are as close to zero as possible. It is not always possible, but if you have one resonance structure that just has a -1 on one thing versus a resonance structure that has a +2 on one thing and then 3 -1s, the one that has the fewest charges is going to be the most stable. And then the second point, the negative formal charge should be on a more electronegative element, and the reverse of that is true. A positive charge should be on a less electronegative element. Pause here. All right, let's take a look at this. We've got 3 different resonance structures of the same thing. All right, so let's take a look at the first resonance structure. So I have sulfur. It has 1 bond and 6 non-bonding electrons, so its formal charge is -1. I've got carbon, which is 4 minus its 4 bonds is 0. And then I've got nitrogen, which is 5 minus 3 minus 2, which is also 0. So let's just do the same thing with the others as well. All right, so I've got all of the formal charges. So I'm going to, off the bat, eliminate the third resonance structure because it has too many charges. When I say unnecessarily high, I mean in magnitude. I don't necessarily mean in number. So then I'm down to resonance structure 1 versus resonance structure 2. Resonance structure 1 has a negative charge on sulfur, and the second one has it on nitrogen. So since nitrogen is more electronegative than sulfur, the second resonance structure is more stable than the first, and the second resonance structure will be the dominant species. So all 3 of these exist. So let's just say, and I'm making these numbers up, it might not be exact, 90% of them are this structure right here, 8% of them are this right here, and 2% are this right here. Or really a better description would be that it's 90% similar to this, 8% similar to this, 2% similar to this. And the true structure is a hybrid, but it is a weighted hybrid, meaning it is most similar to the one that is most stable. Right, here are the additional practice problems for this topic. Thank you so much for watching and have a great night.